Welcome to our discussion on exponential growth. Here are the objectives, right? We want to basically understand how exponential functions work and then be able to model real-world phenomenon with exponential functions. Now, in previous lessons, we've studied growth that goes at a constant rate, which are called linear functions. And then we even looked at growth that occurs with projectile motion, and that's normally modeled by quadratic functions. Now we're going to turn our attention to what's called relative growth, exponential growth, and some of the most common examples of exponential growth are going to be cells and organisms growing in a petri dish type of environment, and then what really matters to most people is money. Compound interest is a version of exponential growth. Okay, so on the day Jeffrey was born, his aunt put $1 in a shoebox for him. Now, each year on his birthday, she decides she wants to put away double the amount from the previous year. So instead of putting another dollar in, she puts $2 in on his first birthday, and then $4 on his second birthday, and then 8 on his third, and so on and so forth. If she continues this trend, how much money will she place in his shoebox on his 18th birthday? Well, we've talked about patterns before and how to recognize patterns, and the easiest thing would be to kind of write out some things and see what's going on. So his age, right, at 0 when he's born, he gets $1, and then at year 1 he gets 2, and then at year 2 he gets 4, and then year 3 he gets 8, and so on and so forth. And hopefully you're starting to see a pattern between these numbers, because if we want to be able to figure out what's happening on his 18th birthday, then we have to know the pattern to figure out what number would go here. Because they just wanted to know how much money she'll put in on his 18th. They didn't ask how much total money was accumulated, although we could hopefully figure out the pattern for this set of numbers as well and be able to know that too. Well, if you look at the pattern, you go 1 to 2, 2 to 4, 3 to 8. Are you starting to see it? That it's just this equals 2 to the n power, where this is n, right? So 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, and so on and so forth. So this would be 2 to the 18th, which is a very large number. Well, if we plotted these points, we would see a great curve like this, and that's actually an exponential curve. So what's the key difference between this example and the ones that we've seen with linear growth? And hopefully you can see that with linear growth, we had a consistent pattern of basically adding the exact same amount each year. So it had a constant rate of change, right? Because it went up by the same amount each year, so its rate of change was constant. Whereas in this example, the amount it goes up each year is no longer constant, doesn't have a constant rate of change. But each new amount is determined by the previous amount, right? We're just basically multiplying each new amount by 2. So that's kind of the key thing to understand with exponential growth is each year's growth is proportional to the previous year's growth. And once you get that figured out, you can see the pattern, right? You can see that its powers of 2. And then you can see that we have this function that's just 2 to the x. And so for any year, we can figure out how much money they put in on that year, which was the 18th, which, like I said, was a very large number. A very generous aunt, by the way. Well, let's see if you can expand your knowledge and figure out this one. So give the video a pause and see if you can solve this skill check. All right, were you able to figure out the pattern that this time you're multiplying each new number by 3, so it's 3 to a power instead of 2 to a power, so you get 3 to the x, and then of course on the 12th birthday you do 3 to the 12th, and it gives you over 500,000. Okay, so exponential functions, we've already seen examples of it. Now we're going to kind of formalize it and say that an exponential function is anything of the form b to the x. We use b because we call that the base. So it's a base number being raised to the x, which is quite different from x raised to a power, right? X squared or x cubed X squared, of course, is a quadratic. X cubed is just to the third power and looks like a lightning bolt, and so on and so forth, right? But those are powers of x, which is totally different. This is an exponential function where it's a number raised to x. And the only rules we have is that b has to be positive, right? It has to be greater than 0, because that makes sense. If it was a negative number, it would jump all over the place, right? Because when x was positive, that would undo the negative, and your answer would be, sorry, when x was even, it would undo the negative, and we would have a positive answer. And then every time x was odd, we would get negative answers. So you would get this function that would jump back and forth across the x-axis, because you get a positive number, then a negative number, then a positive number, then a negative, and it's all weird, right? So b has to be bigger than 0, has to be positive, and it can't equal 1, because if it equaled 1, it's kind of a stupid function. It's no longer an exponential function because you're taking 1 and just raising it to powers, and 1 raised to any power is still 1. So you get the constant function that's just y equals 1, right? This is a horizontal line. So that's not really an exponential function because it's not growing at some exponential rate. So those are the two rules, right? B's got to be positive and it can't equal 1, but it can be any real number. Now, most of the examples we're going to see, B is going to be a whole number, 2, 3, 4, things like that. Sometimes it'll be a fraction, 1/2, 1/3, 1/4, but you don't normally see anything other than that. That doesn't mean they can't exist. They can. X can be anything. It could be 2.7. It could be the square root of 2. It can be pi, right? It can be any real number you want as long as it's positive and not equal to 1. Okay, so here's a second example. A certain bacteria reproduces in such a way that every minute the number of bacteria doubles. So at 8 a.m., or what we'll call time t equals 0. So whenever we start the clock, we always let that be time t equals 0. Suppose we place a single bacterium in a jar at that time, and then we let it start to reproduce. At 8:01, of course, there's 2 because it doubles, and at 8:02, there's going to be 4 because it doubles again, and so on and so forth. Well, we can see that this is the exact same pattern we had with the first money question, where it's doubling each year, or each time period, right? With the money, it was each year. With this one, it's each minute. But it's the same idea, right? Can you see that the function itself is going to be 2 to the x again? So let's see if we can answer a couple questions. At what time will the jar be half full of bacteria? And using what you already know, can you develop a formula to model this data? Now, unless you were really reading what was on the previous slide, you're probably thinking, how the heck can I figure out what time the jar will be half full? Well, I glossed over some information. It tells us that the jar is full of bacteria at 8:30 a.m. So if it was full at 8:30, it should be really easy to answer when it's half full, because remember, it doubles every minute. Okay, but if we want to set it up and figure out the formula, we look at the first few instances and we go, okay, when we started, right, time equals 0, we had 1 bacteria, then after 1 minute it doubled, and so on and so forth. We can see the pattern again, that the numbers on the right are always just 2 to the power of the number on the left, right? 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 2, 2 cubed is 8, and so on and so forth. So if we now know that it's 2 to the x, we can take the time and plot it on a graph, and we'll see that it's exponential. But we really don't need to know that because we know exponentials are always of the form b to the x. In this case, b is 2. Okay, so we know we have a nice little exponential function again. We know that it's 2 to the x. We know that the bottle is full at 8:30. So when is it half full? And be careful, the answer is not 8:15. All right, it's not going to be half full at half of the time, 15 minutes instead of 30. Remember, it doubles every minute. So if you work backwards, doesn't that mean it gets cut in half every minute? So if it was full at 8:30, it's going to be half full at 8:29. As for the second part of the question, we already knew that the function was 2 to the x. I wrote it here as 2 to the t because I want you guys to realize that, x is a variable. We can let any letter be that we want. Instead of it being a function in terms of x, it can be a function in terms of t. And we normally do that when we have functions that are modeled based on time. We use a t instead of an x just to help us remember that the input is time. But there's no rule that says we can't let it be an x. Okay, Again, all the examples we've seen are pretty basic, but exponential functions can get more complex when we throw in the a portion of it. So an exponential function in its most general form is going to be a times b to the x. B is still the base, and it still has those same rules where it has to be positive and can't equal 1. A is now the initial value of our function. Now, in the previous examples, our initial value was always 1. So A was 1. And you don't say 1 times something because 1 times something is just something and it's just silly. We don't list it. But in our previous examples, there were always those invisible, let's say, 1s sitting there. But it doesn't have to start at 1. Let's just look at this example. And instead of starting the clock when we put the first bacteria in there, let's say we started the clock at 8:01 when we already had 2 bacteria. Or we could have started the clock at 8:05 when we had 32 bacteria in there, and it just would have changed it by, that would have become our A. That's all that it really happens, is it's your new initial amount, and it still would have grown at a rate of 2 to the x. So you might be thinking, well, how does that work? Because if it grows at 2 to the x, at 8:06, it should be 2 to the 6th mini bacteria in there. Well, yeah, that's true. We know that the original function was just 2 to the x. And so after 6 minutes, right, at 8:06, it should be 64, which is 2 to the 6th. So if we instead start the clock at 8:05, right, so we're now going to start at 8:05. So when we get here, instead of that being the 6th minute, this is really just minute 1 because it's 1 minute past our starting point. So 1 minute has elapsed. So we can't plug 6 into our function, right? Remember our function, I'm going to write it in terms of t, it's going to be a times b to the t. In this case, if we're starting at 8:05, it's going to be 32 times 2 to the t, right? Because it's still doubling, it's still 2 to the t. But now when we want to figure out what happens at 8:06, that's 1 minute past where we started. So t is 1 instead of 6, right? For the previous function, t was 6, b was 1, and we just, I'm sorry, a was 1, and we just had 2 to the 6th, which was 64. But now t is 1. So we get 32 times 2 to the 1, which equals 32 times 2, which still equals 64. You see how that works? So if we kind of reset the question and give ourselves a new starting point, it's totally fine. Everything works. It's just now when we want to find a certain point in time, that time has also shifted. This is no longer minute 6. This is now minute 1 because it's 1 minute past our new starting point. Okay? All right, how about another example? Now this is more of a real world example where it's not a pretty perfect thing with pretty whole numbers. Now it turns out that this is the function that best kind of matches this data. And there are all sorts of ways to match functions to a set of points, right? If this was a real world example and you just had 8 years of sales data and you wanted to figure out a function that modeled it, you're basically just trying to fit a curve to these dots in space. And there are all sorts of very fancy computer programs that can do that for you. And even simpler ones, a lot of graphing calculators can even handle this. StatCrunch can handle this, but I digress. If you want to try and do it by hand, remember that with an exponential growth function, the differences are not the same, right? We're not adding the same amount each time. And we can see very clearly that we're adding almost 110, right? And then we're adding almost 140, and then here we're adding 280. So we're not adding the same amount, so we know it's not a linear function. So then you got to ask yourself, okay, am I multiplying by something? 55 times something equals 162. And that same something, if I multiply 162 by it, it should be 300. And if you do that math for all of these pairs, right? 55 times what is 162? 162 times what is 300? 300 times what is 580? And see if those answers are very close. And if they are, that becomes the base of your exponential. In this case, it comes out to be almost 1.9, right? Once you have that in place, then you figure out, okay, what's the initial value? You would think the initial value should be 55, but that's at year 1. you want to figure out what happens at year 0, right? When you first start the clock. So when you put a 0 in for here, this goes away and you would be left with this amount. So it's kind of like working backwards, and whatever this amount was, if you divide 55 by it, that'll give you your starting amount. And that's what's really happening here with this, and that's, what the computer program does to determine the thing that fits our data best. And then this will allow us to answer questions like, what do we think our sales will be in year 15? Or how much total money will we have over the first 20 years, and all sorts of different types of questions. It all relies on you being able to come up with that basic exponential function. Okay, our last example, we've got a certain town had a population of 2,000 in 2001. That's a little confusing. And if the population is increasing at a rate of 2% per year, what will the population be in 2021? Well, first of all, you got to figure out that 2021 is how many years down the road from 2001, and it's 20 years. So X, or T, whatever you want to call it, our time is going to be 20 years past. The base of our function, right, if it's growing at 2%, then we have 100% of it plus whatever that growth rate is. So this is a standardized formula for exponential growth when we're given a percentage. And this is the kind of formula that you use for compound interest. So R stands for rate. It's the rate of increase. And in this case, because it's 2%, it's 0.02 as a decimal. A, like it always is in exponential functions, is our initial amount. And if we're starting with 2,000 things, right, in 2001, which is, year 0, then it's 2,000 for A. And then 2021 is 20 years beyond that, so that's our 20 there. If we plug everything into our function, we get 2971.89, or if we round up, because we got to round up to, you can't have 0.89 of a people, you round up and you say there should be roughly 2,972 people, or a little less than 3,000 people after that 20 years, or i.e. in the year 2021. And that's our last example. Hope this helps you guys figure out what's going on with exponential growth stuff.